Welcome to this third session. Last time we were looking at the Aufbau principle and looking at the sequence in which subshells were filled in the periodic table. And then we went on from there to look at electron configurations and how we describe it in terms of each subshell and the electron occupancy of that subshell, the maximum capacities of these subshells, and this peculiarity that we were filling the 4s subshell before the 3d subshell after we'd gone past argon. Then we did a similar kind of thing for ions, and then we identified a couple of exceptions, and these were in the first row of the D block. Chromium and copper didn't fit the rule, and there was a kind of way of rationalizing that. And so now we're going to put that into practice with a few exercises and see if we can write the electron configurations for some atoms, some ions, and then in the fourth row of the periodic table, getting used to putting them down using a noble gas core. So just pause the video, have a go at these. You've got the periodic table to refer to there, and I'll give you the answers in just a second. Here we are. So here we have our answers there, having written out the electron configurations in full for the first couple of sets, and then from argon at the bottom. And the point I was going to make about the ions, oxide, fluoride and sodium ions all have the same electron configuration. So in the second row, oxygen and fluorine had filled their outer shells to give the noble gas configuration for neon, and in the third row, sodium had emptied its outer shell, forming a positive ion, also leaving the neon noble gas configuration. So that's quite an interesting thing with ions, and we would call them isoelectronic. So isoelectronic means you've got the same number of electrons in the same orbitals. And so, I mean, you may wonder why it is then that these ions don't resemble neon. And so the important thing to remember here is that all of these ions have an electric charge, and then having an electric charge means they're involved in ionic bonding. Whereas in the case of neon, of course, there's no charge. So in the absence of any ionic bonding, and there's no covalent bonding either, they're very weak forces between the particles, and it's just a gas. So now we move on to the ionization of transition metals. And up until now, when we've been ionizing atoms, we've, as it were, removed the last electron we've put in as we fill the atoms up with electrons in the periodic table. Clearly, when we ion, if we're looking at the ionization energy of an atom, we are removing the electron which is at highest energy, because we ionize an atom by using the minimum amount of energy, which is going to ionize the electron. So it's kind of last electron in, first electron out. It's the kind of principle that we normally use. But we actually see the opposite thing happening with transition metals, which is to say that the 4s electrons are ionized before the 3d. But of course, when we fill the atom up, when we get past the 3p subshell, we put electrons into 4s before we put them into 3d. So this is unexpected. This is not the order that you'd predict from the Aufbau principle going backwards. And really, this is normally something that a chemist would just accept as a fact and just learn it. But it does cause quite a bit of confusion and head scratching. And so a couple of questions that pop into people's minds might be, why actually would the 4s subshell be filled before 3d in the first place? We'd expect the third shell to be lower in energy than the fourth shell. And I think a good explanation for this is you could say that the third shell already has 8 electrons in it. Once you've got up to argon, you've filled the 3s and the 3p. And so if you were to put an electron, the next electron, into the 3d subshell, it would be in the third shell with 8 other electrons. And putting a 9th electron in there with those other 8 actually involves quite a lot of electrostatic repulsion between those electrons. And electrostatic repulsion, this will raise the energy of the electrons. There's kind of an energy cost in creating all that repulsion. And so it turns out that for the potassium and calcium atoms, if they promote a 3d electron up to the 4s subshell, even though that would require an input of energy, overall there's a saving for the atom because there's much less repulsion energy with the other 3D electrons. So there's a net energy benefit, as it were, from putting the electron in 4s rather than in 3D, and it's explained in terms of all these electric repulsions. Another question could be, this is a harder question actually, looking, there's a kind of a paradox here. When you compare the ion configuration, 4s2 3d6, as we've come to know it for the ion, the 26th element there, 80 electrons outside the argon core, filling the 4s before the 3d. So we know iron is 4s2 3d6. If you compare this with nickel 2+, so nickel is 2 elements after iron, so we've got 10 electrons outside the argon core, so we know that the nickel atom will be 4s2 3d8. But we learn that for ions we lose the 4s electrons first, so nickel 2+ we'd predict to be 3d8. And this is quite problematic because, of course, nickel, having lost 2 of its electrons, nickel would have the same number of electrons now as iron. And so we've got 2 species with the same number of electrons and yet different electron configurations. So this really does seem quite odd. So we've got 4s2 3d6 in iron, 3d8 nickel 2+, same number of electrons. How can we explain this? And I think the answer to this question, in fact it has to be, I think, really to do with the protons in the nucleus, because there isn't really any difference other than the protons in the nucleus. So nickel, being element 28 as opposed to element number 26 for iron, has got 2 more protons in the nucleus. And so I think when you have more protons in the nucleus, this ramps up all the electrostatic forces involved, and therefore with the higher atomic number all the energy levels are more spread out. So in other words, in the nickel case there's going to be a bigger energy gap between the 3d and the 4s, so more energy will be required to promote d electrons up to the 4s subshell, and that's the reason why the electrons, all 8 of them, stay in the 3d, because there would then be a net energy cost to promote electrons up to 4s. And I think one thing that's remarkable about this is how the change in atomic number is enough to change the electron configuration that's observed. So it just goes to show really what a finely balanced thing it is, and often there are very small energies involved between the different configurations in this part of the periodic table. So now there's a little exercise for you to do here on transition metal ion configurations. So if you can remember those rules we were just going through, and you can see up at the top there I've reproduced that little bit of the periodic table so you don't have to look it up. So you need to find the atom along the row, think what the electron configuration is of the atom, then you're going to have to remove a certain number of electrons depending on the charge and apply those rules as well. So have a think about that, pause the video, have a go. I'll give you the answers in just a second. So here are the answers there. So you notice that on the screen here there isn't a single 4s electron anywhere, and that's because in all these cases the charges on the ions are all 2+ or more, so that means you're definitely going to be emptying the 4s shell. And in fact there's only one of these elements really forms a 1+ ion, and that's copper. And of course you remember copper had the electron configuration 4s1 3d10 in the atom, and so that only needs to form a 1+ ion to empty all its 4s electrons out. It's only got the 1 4s electron. So what that tells you then is that these transition metal atoms don't form any ions at all which have a 4s electron. So all their ions involve just d electrons. Now on to the next thing, electrons in boxes. And this is really taking our electron configurations a little bit further. So up until now we've been writing them in the form 1s2, 2s2, etc., where we simply indicate the number of electrons in each subshell. But we're going into greater detail with electrons in boxes, because rather than just subshells, we're going to look at the orbital level, what the occupancy is in specific orbitals. And so in taking this approach we need to apply some extra rules. So you can see up there I've written out the orbitals up to, I suppose, calcium. So there's the first 20 elements worth there. And so the shells there are expanded into the orbitals. So notice that in the p subshell, where we've got 3 orbitals for each subshell, the orbitals are labelled by one of the axes, x, y, z. And this is the axis along which the dumbbell points. And you remember we can get 2 electrons in these orbitals as long as they're opposite spin. And so we indicate spin up with a single-headed arrow pointing up, and spin down with a single-headed arrow pointing down. And there's quite a bit of convention going on here. So some of it seems slightly arbitrary, and I suppose it is really. So for example, when we're putting electrons in, I mean, obviously we'd start from the lowest energy shells. And so in this picture here, we're essentially going from left to right, putting the electrons in. And when we've got choices to make, there are certain conventions. So when you put the first electron into an orbital, by convention, we show it as a spin-up electron. And of course, in just a sort of isolated atom, it wouldn't make any difference to the energy or anything if it was spin up or spin down, but this is the convention that we follow. Where we have multiple orbitals in a subshell, like in a p subshell, we would just start from the left, spin up in the first orbital, then the second electron would choose to go in a different orbital. And the idea is that there's more repulsion if 2 electrons are together in the same orbital, so they'd preferentially go into different orbitals. And so the second electron would go into the second orbital, and by convention we'd have this spin up as well. So the third electron will go into the third orbital, spin up, and it's only when you get to the fourth electron that you have to pair it up. And so again, we go left to right, and you'd put the first spin down electron into the orbital on the left. And I've got an example coming up here of nitrogen and oxygen. So in the case of nitrogen here, I've got 1s2, 2s2 electrons in there. And when we start filling the 2p subshell, they go in, so the first one in the first orbital spinning up, second one in the second orbital spinning up, third one in the third orbital spinning up. So this is our nitrogen electron configuration in the form of electrons in boxes. So you can see how it's carrying just a bit more information than the ordinary electron configuration, because it shows, I suppose, 2 things about the electrons. Firstly, they're in different orbitals, which we didn't know just looking at 2p3. And secondly, that the spins are all parallel. And of course, there's no information about the direction of the spin in the ordinary electron configuration. And then when we look at the next element in the periodic table, oxygen, with 1 more electron. So again, 1s2, 2s2, and then we'd sequentially fill the 2p orbitals in just the same way. And then when we've got our final electron, our 8th electron, there you go. So it goes spin down into the first orbital on the left as we fill up the subshell. So this is the system that we use to show electrons in boxes. And so we really are looking at the finest detail possible at this stage of the electron configuration, exactly what the electrons are doing as far as orbitals are concerned. So there's a little exercise here for you now on electrons in boxes. So I'd like you to try and complete these electrons in boxes configurations, and we'll just stick to the subshells outside argon. So obviously the argon core is going to be the same for all of these. So there you go, we just assume we've got 1s2 filled up to 3p6, and then these are the electrons outside. Okay, so I'm afraid I've not got a periodic table, I don't think, have I, on this slide, so you'll just have to remember. So what? Iron's element number 26, manganese is 25, and copper's 29. So you could pause the video, I suppose you could go find yourself a periodic table, work out the electron configurations, draw it in, then come back and I'll give you the answers in just a second. So here are the answers. There we go. So first up, the electron configurations in the sort of shorthand form, and of course, as we saw before, all of these ions having no 4s electrons. So typically you wouldn't have to write 4s0, but I'm just making the point, I'm just emphasizing there are no 4s electrons, even with the copper 1+, as you can see. And so all of those 4s orbitals are empty. So really it's the 3Ds that we should be thinking about. And so there we go. I've got all the subscripts there on the 3D orbitals that are used to identify them. And I've filled from the left. And so, for example, on that middle one there, manganese 3+, where there's a smaller number of electrons than there are orbitals, you can see I've just started from the left and put spin-ups in. Then when it got to 3D6, in the top first example, you can see that the first 5 electrons filled all the orbitals with a single spin-up electron or parallel, and then the 6th electron is forced to go spin down, and we put it in the left-hand orbital. Now, I mean, the order, if for example, the order in which you write the names of the orbitals doesn't have any significance. So there's nothing special about a dxy orbital compared to a dxz, for example. And likewise, when we're looking at the p subshell, you know, I wrote them px, py, pz, but really they're all the same energy, they're all equivalent. There's no special reason why the x would have to take the electron. It's just I've just put them in alphabetical order. It's just a kind of conventional way of doing it. Of course, with these orbitals all being in the same subshell, they've all got the same energy. And in a way, it's kind of meaningless for an isolated atom to say which orbital is the electron in any way. So as I say, it's just a kind of convention with all of this. So when we get to copper plus, that's 3d10. And so actually with 3d10, what we have is a full subshell. So each orbital there is doubly occupied. Now we come on to the topic of ionization energy. Now this is a really important one in chemistry, and so we'll go through this quite carefully, defining everything. So first, ionization energy would be a good place to start. And so let's have a look at this definition. There's several important points in there. So firstly, it's the minimum energy required to move an electron. And so there are many energies that will remove electrons. You might remove an inner electron, or you may remove an outer electron, and once it's out of the atom there's lots of energy to spare, so the electron goes off really fast. But the critical energy really is the minimum energy that's required to remove an electron. So it would have to be, if you like, the outermost electron, the electron at highest energy, and it would be the energy that's just required to remove the electron. So it would be taking it to its ionization limit. It's like the infinitieth shell. So it's that minimum energy that we're after. And it's also very important that it's done in the gas phase. And this is really just to keep life simple. In the solid and liquid phases, we've got complications to worry about. There's bonding. You've got, intratomic, intermolecular forces. Life's much more simple in the gas phase, where you have just an isolated atom. So these are all properties of isolated single atoms in the gas phase, where we can just look at the most simple interactions, basically involving the electrons and the nuclei. And finally, it is a molar quantity. And so it's the minimum energy to remove one electron from every atom in a mole of atoms. And the reason for this is that for a single atom, the energy will be absolutely tiny, which makes it inconvenient to be able to use tiny numbers all the time. But once you multiply that tiny number by Avogadro's number for a mole of atoms, then it's a fairly sensible number that's easy to work with, and it will give us something in kilojoules per mole, which is the unit that we typically use for energies in chemistry anyway. So that's our definition of the first ionization energy. And actually, following on from this, there are further ionization energies that we should know how to define as well. The second ionization energy is removing the second electron, going from a 1+ ion to a 2+ ion. So it's not the energy required just to make a 2+ ion, but it's making a 2+ ion from a 1+ ion. And the rest of the definition is the same, so it's the minimum energy, it's in the gas phase, it's a molar quantity. And you can see this is summarized here in this little equation, m plus gas going to m2 plus gas plus an electron. In fact, we can have further ionization energies after this as well, third, fourth, fifth. And so in general, you could say that the nth ionization energy would be the minimum energy required to move an electron from every mole it will be the n-1 plus ions to form the n plus ions. And so there you go, that's a kind of generalization. We get a lot of these ionization energies quoted. And to really illustrate what I mean by the minimum energy required to remove an electron, I've just sketched a little diagram here, and I happen to have used the case of beryllium. So you can see on the left hand side there we've got the beryllium case, and so the electron configuration of beryllium is 1s2 2s2, and I've put this on an energy axis. So you can see we've got an energy axis there on the left hand side. This is roughly to scale, this sketch. And so in the case of beryllium, the minimum energy required to ionize the atom, you're going to be having to take one of the 2s electrons, so that you can see these are the highest energy electrons, and you're going to have to give it a little bit more energy to take it up to the so-called ionization limit, which we have there with a dotted line. This is the equivalent of taking it to the kind of infinitieth shell. And so that little small gap I've indicated as the first ionization energy there in green, that will be the little jump that an electron has to be given, the energy they have to be given to get up to the ionization limit. And I've just gone on a little bit further on the diagram to talk about what would happen after that. So after you've ionized beryllium, you end up with Be+, which would only have 3 electrons. And you can see next to beryllium on the picture there, I've sketched in what's roughly going to happen with Be+. And when you look at it, you see that above Be+, we've only got 3 electrons. Obviously we've ionized one of them now. And you can see that the 2s level has only got 1 electron in it, having ionized one of them. But we also see that the 2s level has gone down a bit in energy. And this is because the electrons shield each other slightly from the nucleus. But that one electron in the 2s subshell, it no longer has a partner electron to give it a little bit of shielding. So it feels a bit more nuclear attraction, and that pulls it down in energy as it's attracted to the nucleus. And you can see on the picture now that remaining 2s electron needs a bit more energy than the previous one did to get to a kind of escape level, the ionization limit. And so this reflects the fact that there's less shielding going on of that electron. And so we see there that the second ionization energy is a bigger jump than the first. And having done Be+, I thought, well, let's look at what happens after this. So then next along, you can see we've got Be2+, where there's just 2 electrons on the atom now, and they're just in the 1s subshell. And because the 1s is a lower shell, much closer to the nucleus, then there's a much bigger jump, a much bigger amount of energy is required to take it, up past the energy of the second shell, all the way up to the infinitieth shell. So as you can see here, the shell energies are converging very rapidly. It's quite a big jump to get from the first shell to the second shell, and then very much smaller jumps to the higher shells, and the ionization limit kind of reflects the infinitieth shell. And so once you put that larger amount of energy in as the third ionization energy, that would take you to Be3+. So with Be3+ here, you can see on the right hand side you've just got 1 electron left in the 1s subshell, and again you can see the 1s subshell is drawn at lower energy. So again, this reflects the fact that that lone electron there, it doesn't have any other electrons to shield it from the nucleus, so it's pulled in and attracted more closely to the nucleus, and that means more energy needs to be put in to liberate the electron. That's why we've got a bigger jump there, labelled fourth ionization energy, to take it up to the ionization limit. So that's an interesting property actually. When you compare all these different ions, you can see that the energies of these subshells isn't constant. It actually depends on the other electrons in the atom. But the one thing we can show as being constant is actually the ionization limit. And interestingly, because it's a constant, we actually define it as 0 in energy. Well, actually, it's not always defined as the 0, but I mean, most of the time for our purposes, we'll define that as 0 in energy, which is slightly odd then, because it does mean that all the electrons in the atom are given a negative energy, as you can see on the y-axis there on that graph. So there you go, that tends to be how it's done. The energies tend to be negative, which is illustrative of the fact that the ionization limit we're defining as 0. So on the previous slide, we defined ionization energy and then went on to define the higher ionization energies and also considered them in terms of an energy level diagram. And this kind of sets us up now to look at successive ionization energies in general, and in fact in the specific case of an element. And so you can see on the slide here, we've got the successive ionization energies of copper plotted. So these are all experimental values. There's an awful lot of ionization energy data that you can look up for lots of elements. Now copper is element number 29, 29 protons, 29 electrons. And it's actually possible to look up all 29 ionization energies. So by the time you've done the 29th ionization, there are no electrons left. So that's the absolute limit. So, you know, copper 29 plus is just a nucleus with 29 protons in and a whole bunch of neutrons and no electrons at all. And so it's important that we can look at a graph like this and make some points about what's going on. So what can we say? The first general point we can make is that these energies are always going up. So a successive ionization energy is always greater than the one before. And how do we rationalize this? Well, we mentioned a little bit before, didn't we, in the last slide, the business of shielding. So as electrons get taken out of the atom, there's less shielding for those electrons that remain. And if they're being less shielded, they're being pulled in closer to the nucleus, and so more energy is required to liberate them. Another way of looking at it is that as you do successively higher ionizations, then you're dealing with a more highly charged ion. So for example, if you were trying to, if you had like a 10 plus ion, then it's going to take, there's going to be a lot of electrostatic attraction between a 10 plus ion and an electron that you're pulling off it. And even more so if it was a 20 plus ion and electron you're pulling off it. So just on the basis of that kind of sheer electrostatics, you'd expect a higher and higher energy demand. So yeah, just to remind you, all of these are necessarily endothermic processes, because in every case, as we saw in the previous slide, you've got to put energy in to get the electron up to the ionization limit. Another way of looking at it as well is the kind of proton-electron ratio. So when you do lots of ionizations, then having removed many electrons from the atom, clearly the protons are going to outnumber the electrons. And so in general, if you've got a lot more protons than electrons, you'd expect, as it were, the protons to win out and the electrons to be pulled in very close, and therefore requiring a lot more energy to remove. So that's the general case then about why this goes up. So I'll make this point here with the text that's just come up about the energies going up. And in fact, one point is worth making about this is if you look at the units on the y-axis, it's not just ionization energy on the y-axis, we're actually plotting the log of the ionization energy. And we tend to do this plotting of the log when the thing you're plotting is going up extremely quickly. And so in fact, if we just plotted the ionization energy, this would go up. It goes up so extremely high that actually you wouldn't even be able to see what's going on at the bottom of the graph once it was all on an ionization energy scale. So in fact, what we're plotting there are the powers of 10 of these ionization energies, which just shows you how fast they're going up. Right, and so there's another feature, in a way the most interesting feature of the graph. You can see that not only is it going up all the time, but there are some discontinuities, aren't there? There's some discrete steps. And really the most obvious step there is towards the top right of the graph. You can see that the top two ionization energies, which will be the 28th and 29th ionization energies of copper, are distinctly higher than the 27th. And so this is the point I'm just making in the text here. So if you think about it, once you get down to the 28th and 29th ionization energies of copper, you're down to the last two electrons in the atom, and these are going to be the 1s2 electrons. So it's a bit like a helium core, helium being 1s2. And so it's not only like trying to ionize helium, which of course has a very high ionization energy anyway, but it would actually be like a helium atom with 29 protons instead of 2 protons. So that's why these are extremely high ionization energies. And of course we know in chemistry that noble gases are very unreactive, and this reflects the fact that they've got these closed shells or closed subshells. And so if you like, the unreactivity of the noble gases is kind of manifest in these pictures. So the big step up from the 27th to the 28th ionization energy kind of reflects the unreactivity of helium. And you can see there's a similar thing going from the 19th to the 20th ionization energy there. And this actually reflects the unreactivity of the next noble gas, neon. So once you get to copper 20 plus, you've effectively got a neon electron configuration. So being a noble gas there, it's much harder to ionize than the copper 19 plus. And the reason for that is that the copper 19 plus will have one electron in the third shell. So it's a bit like it's the sodium configuration, isn't it? So it's sort of relatively easy to ionize sodium compared to ionizing a neon. And of course, once you've ionized that 3s1 electron from sodium, you're then having to go down a shell. So once you go down a shell, you're then much closer to the nucleus, where the electrons are held in much more tightly. And that's why you get this jump in energy from the 19th to the 20th ionization energy. So that 20th ionization energy there, you're basically ionizing neon. And then you can see you've got that row of 8 dots there between 20 and 27. And this essentially, it's like going across the second period. So, after you ionize neon, you then kind of be onto fluorine and then oxygen, then nitrogen, etc., working across the period of those electron configurations. And then when you get to the 27th ionization energy, on the right hand side there, you'd be ionizing lithium. And then you get the big step up when you're going down from the second shell, 2s1 for lithium, down to that 1s2 helium core. And it's quite interesting because then you work into the left again. So we said that the 19th ionization energy there was a bit like ionizing sodium. Well, as you work along from the left, and then you get to the 12th ionization energy, so you can see the 12th there is quite a bit higher than the 11th. Well, actually, there's a little step, isn't there? It's not as big as the two to the right, but there's definitely a little discontinuity there. And actually what's going on there, as you step up from the 11th to the 12th ionization energy there, that's going to represent the ionization of argon, of course the next noble gas going down. And then, so what do we have before that? Well, the 11 ionization energies we have before argon, this reflects the 11 valence electrons outside argon, because of course the electron configuration of copper is argon 4s1 3d10. So in fact, when we go right to the beginning of the graph, the very first ionization energy there on the far left at the bottom, that will be ionizing your 4s1 electron. So you can see that after ionizing the 4s1, there is actually quite a big step up there. So you can think about that. That's a bit like, because you're basically going from the fourth shell to the third shell, aren't you? So the first ionization energy takes off the 4s1, then you're down to the 3d subshell. It's going across the transition metals, and so you've got the 10d electrons, or the next 10 dots, that you're taking off. And so once, so that 11th ionization energy there, that'll be ionizing potassium. Well, actually that's not quite right, is it? Because we take the 4s electron off first, don't we? So actually it'll be a little bit like ionizing scandium. But it is quite a small jump there, and I think this reflects the fact that even though we've got down to a noble gas core, actually we've been ionizing 3d electrons, and then we're moving on to 3p electrons. And so I think that doesn't reflect quite such a jump as it does in the top two noble gases, looking at the helium and neon cases, because in those cases not only is it a noble gas, but you're also dropping down a whole shell. Whereas going from the 11th to the 12th ionization, really we're going from 3d to 3p, aren't we? So I think that's why it's a smaller jump. So that's how we're interpreting the graph, how we interpret the discontinuities. And a couple of extra things to say about this. The next point is that this is actually very interesting from a historical point of view, as evidence
for the electrons being in shells. So you may remember that the big evidence we referred to before was the hydrogen emission spectrum, where we get these clear series of convergent lines which pointed very strongly at a series of electron shells. So that seemed to be a kind of slam dunk for this shell model of atoms. But you see, really, that only really applied to hydrogen, because in multi-electron atoms the spectra are much more complicated. It wasn't so obvious. So while we only really had evidence for hydrogen before, these successive ionization energy plots, these will be indicative for all other elements, all multi-electron elements, that all of them appear to have a kind of a shell structure, where these discontinuities reflect the shells essentially going into inner shells. So I think it's quite interesting from a historical point of view in terms of evidence of electron shells. And the final thing to say is just to kind of build you up for the next slide. And in our next slide, we're going to kind of go through this process backwards. Because you see, in this case, we know the element is copper, and we're trying to rationalize the appearance of the graph. And then the skill which you've got to develop is that one where you're presented with the data for an element, but you're not told which element it is. And so what you'll be doing when you're presented with the data is, of course, you're going to be looking for these big steps. And these big steps are going to give you the information that you need to answer the question. Here we go. So here's our exercise. And so what you've got in the table here are a series of successive ionization energies for a mystery element, all values in kilojoules per mole. And so it's a multiple choice. So beneath, I've given you 5 choices of mystery element. And there are the numbers. So I've not put the numbers on a graph. And so very often in a question, you won't have the numbers on a graph. And to be honest, it'll be a bit time consuming to plot a graph. So hopefully you can just look at the numbers and just appreciate that they're not going up in a totally regular way all the way. There's actually a few big steps, or at least, have a look out for it. So I'll leave you to think about this for a second. Look at the numbers, try and think where the steps occur, and then think how that might correspond to the nature of the atom giving that series of numbers. So yeah, pause the video, have a think about it. I'll give you the answer in a second. So here we are. You can see here I've plotted the graph just to really make the point. But you see, just looking at the numbers, it should be clear enough. You're going from roughly 800, 1600, 3200, 4400, 16,000, 20,000, 24,000, 30,000, 34,000, 39,000. So you can see they're going from the 4th to the 5th ionization energy. That's sort of roughly multiplied by 4. That is a much bigger step than the others either side of it. So yeah, as I say, just make it clear here on this plot. But I don't think you really need to plot it. It should just be obvious looking at the numbers. There's a big jump from the 4th to the 5th. So how do we interpret this big jump? So the way we do it is we say that this is probably an atom with 4 electrons in its outer shell. Because once you've removed the first 4 electrons and you've emptied the outer shell, you'd expect the 5th ionization energy to be much higher, because you're having to go down to the shell beneath it. And so in the 5th ionization energy, you'd be trying to ionize a noble gas core. So we deduce then that we're looking at an element in group 4, as you'd call it in GCSE, where you'd find 4 electrons in the outer shell. So you may remember that of the options that we gave you, there were actually 2 elements in group 4, carbon and silicon. So on the face of it, it might seem like a bit of a trick, because you might say, oh, how can you distinguish which one it is if they're 2 atoms that are both in the same group? But there is a little bit of a trick here, because of course carbon is element number 6. It's only got 6 electrons. So there's no way that you could possibly have data for a 7th ionization energy of carbon. It's just a non-starter. And so therefore that eliminates carbon as a possibility. So it would have to be silicon. But it's true that if you were asked to choose between silicon and germanium, for example, germanium's also in group 4, that would be kind of an impossible question. You'd actually have to go and check the data book, because you'd expect all of those to step up in this way. So there you go, that's the answer to that problem.